Okay, so let's talk about this calibration technique. So this technique is consistent with our textbook, but it's slightly different from what's in our textbook, but is the one that's been established by various instructors at Cal Maritime for use in the labs. So you should learn this one because you'll be using it in future classes. So here's the goal. We have data that we've taken. I'm assuming it's a temperature calibration here, but it could be any kind of sensor. So we're measuring voltage, the output of the sensor, and the voltages are for a given known temperature. So we know the input, and then we measure the sensor output, and for each known temperature, T actual, we're taking many voltage readings, several measurements of that temperature, and so we'll get different voltages there. So the data setup is that we will have NT temperatures, and for each temperature we'll take NV voltage measurements. The final result that we'll get is a calibration so that someone could use our sensor, take a voltage reading from it, and turn it into a temperature. So they'll need a curve fit line, a slope M, offset B, and then the other thing that we're going to get is an error analysis for the uncertainty in a future single measurement with 95% confidence using the statistics of our calibration. So the two error components we're going to calculate are precision error, P, that's a measure of the randomness in our measurements, and then bias error is a measure of the systematic error. We'll use B for bias. On the last page of the handout, there are a couple of examples of what data could look like. So here we have a voltage measurement on the y-axis, known temperatures on the x-axis for our calibration experiment. This top plot has got a lot of randomness. You can see the scatter in the data at each temperature. We've got a pretty wide range of voltages, and averaging them, the average is the red circles, brings things into much better alignment. So averaging helps. That means it's mostly random error here. So this is a large P, random error, that component of the total error, and the B, the bias, is small because after averaging, our averages are pretty close to the actual curve fit of the data. This other plot is the opposite in terms of which component is larger. So here our measurements are very tightly grouped. There isn't a lot of randomness. It's very repeatable, but it's not very close to the line. So averaging doesn't really help. So the random error, the precision error is small, but the bias error, which is a measurement of how close the mean and the curve fit are, that error is pretty large because it just isn't a very straight line, and averaging doesn't make it any straighter. So we can put a line through it, but we'll end up with a fairly large bias error. So taking a look at some sample data here, we've got, this is an Excel spreadsheet, and we've got the known temperatures here in the first column, and we've arranged our voltage measurements. We're taking 3 voltage measurements at each temperature, so this isn't a very large number. Usually you'd have quite a large number here of measurements because it's easy to do. We're going to take 3 to make the analysis simpler, and we're calling them cycle 1, cycle 2, cycle 3. So this is voltage at each temperature. And we can arrange it like this with one column for each cycle. That's a better form for some of the analysis, but we can't do a curve fit in Excel anyway with the data in this form. For the curve fit, you need everything in 2 columns, so Excel does the right kind of curve fit. So we'll see that in a little bit. Okay, so we're just going to go step by step through this handout. So the first step is to arrange the data as we've got it arranged. So a row of measured voltage for each temperature. And again, we get NT temperature rows by NV voltage columns. And usually you're copying and pasting. So then the first calculation is to find the mean voltage for each temperature. We're going to call that V bar. So here is our data. And the first thing is to do V bar, the average temperature. So we can just do average of all of these things. So we're just averaging across the rows. Copy that down. So that's our average voltage measurements. That's step 2 in these instructions. The next thing is to calculate the deviation, and deviation is always a difference, and here we're doing the deviation from the mean at each temperature. So we're going to find the voltage. The deviation voltage is the individual voltage measurement minus the average, and so we'll get a matrix the same size as our measurement matrix. So here is where we're going to put the deviation calculations, and so it's just each one is the individual voltage measurement minus the average, and if I put a $sign in front of the column, it will keep it from moving, and I can propagate that across. So this one is based on cycle 3 minus the average. This one is cycle 2 minus the average, and I can propagate these down. So this is the deviation data, deviation from the mean. Sometimes we do deviation from the curve fit, but this is deviation from the mean. So the next step here is to find the standard deviation of the deviation. And we can do that all in one using stdev in Excel. If you're doing it in MATLAB, it's std. And we're going to call that sigma 1, and it is going to help us with the precision error, which is how random the individual measurement is. It's important to keep track of the units, so the deviation is in volts, so the units on sigma 1 are going to be volts as well. Just grab all of that data, put it down. Okay, so I've calculated sigma 1 standard deviation of the deviation matrix. So we've finished step 4. So the next thing to do is we want to find the curve fit of our data. So what we have to do is we have to go back and change the format, or maybe it was originally in this form. We need one column for voltage and one column for temperature for all of our measurements. So we have to copy and paste if we don't have it already in this format. If you curve fit it in the matrix format in Excel, it's just going to curve fit one of the columns and you'll get the wrong, it will look pretty close, but it'll be the wrong number. So our goal is to find the calibration curve to take a voltage and calculate a temperature. And that's the backwards format of the natural curve fit line. So we'll just use algebra to solve for it. So here I've pasted all the data. So here's my first column, repasted all of the temperatures, and the second column of voltages, same temperatures, and the third column. So just going from the cycle 1 and these things and pasting them down into this form. And if I do that, I can graph them in Excel. Always scatter plot. And if I right click, I can curve fit, and you can see it selects all of the points when I add the trend line. So I want a linear trend line. I want to display the equation on the chart. So this is my curve fit. This is voltage as a function of temperature. So Y is voltage, X is known temperature, and I want to flip that around. So I actually want to solve for X in terms of Y. So I can do that. Okay, so these are the numbers that I got from my curve fit solving for the so Y plus 3.83 divided by 4.8 gives me the equation, and I can turn that into my slope and offset. So then we're going to use our curve fit to find the temperature that would be predicted by the mean voltage, and we can use that. That's going to tell us how well the curve fit compares to the actual known temperature, and we can use that to find the bias. So we want to calculate T fit, which is M times the average voltage plus B. So here I can just say equals M, and I'll put $signs to lock that in. You could also name it or something. M times V bar plus B. Again, I'll put $signs here to lock it in place. So now my pattern is to use this one according to the placement, but these are fixed. And if I copy it down, you can see that the middle one uses the middle one, but it's still using these two here. And as a check, this is temperature from our curve fit, and it should match pretty closely to the known temperature here. You can see it's pretty close. So we found T fit. It's got NT values, and they should be similar to the original known values. And if we plotted those, we'd get the curve fit line that's already plotted, so we don't need to. And now we're going to calculate the difference. The error here is the T fit minus the actual. So T fit minus T actual is just T fit minus T actual. And hopefully these are small numbers. All right, so we've calculated the error, that's step 7. And now the last calculation is to find the standard deviation of this column, and that's what we're going to call sigma 2, and it's related to the bias or systematic error. So the standard deviation of this column, this is in degrees because it's temperature. We'll call that S2 in here, sigma 2 in the handout, and that's our other major outcome of this. Okay, so to put everything together, we have on the second page of the handout, for 95% confidence, a single measurement will be within 2 standard deviations of the mean, and we'll use that to estimate the uncertainty. So P, the precision uncertainty, is 2 times the standard deviation. This would be in volts. S1 is in volts. So to convert from volts to temperature, we use M from our curve fit, because that's how many degrees per volt we have. So 2 sigma 1 times M is our P. Two times sigma 1 times M, and that's going to be in degrees. Okay, so for B, the bias, we're using twice the standard deviation again. This one's already in degrees, S2, so we don't need the unit converter of M, so 2 times S2 gives us the B. B equals 2 times S2. Degrees. Okay, so those are our 2 components of the error, total error, or the total uncertainty with 95% confidence. So we're almost done here. So the overall uncertainty is W, and it's the square root of B squared plus P squared. And then our calibration curve comes from this equation here. So let's calculate W. So here's our W, calculated with these 2 things, and 0.2486 degrees is our answer. You can see that it's mostly P, not so much B. Often there's one more than the other. So this one's more random than biased in our case. So our final result, T equals M, so that's our slope, times any voltage that we get, plus our offset, and the uncertainty is plus or minus 2, 4, 8, degrees. So this is what we would tell our customer who bought our system. Now they can take a voltage, they can convert it to temperature, and they can know the total uncertainty. All right, well, I hope that worked for you. And this is just as easy to do in MATLAB, maybe even easier if you're going to do it on a lot of different data sets, because you can run the script without having to copy and paste and things. So consider doing it in MATLAB. Excel's a little better for the visual presentation, so I did it here. Let me know if you have any questions.